Students, let us solve the fourth question of this paper. Show by counter example that the statement f of n is equal to 5 by 2 n cube minus 5 by 2 n square minus 19n plus 20 is a perfect cube for all positive integers n is not true. So we need to prove that by counter example that this is not a perfect cube always. Okay, so I would say you can use a trick over here in your calculator, but you need to show the detailed working later on. If you're using a calculator, in some of the calculator it would be in the option of table, or in some calculator it will be having an option called function where you can enter this whole function. Okay, so first you enter the function. You would have to enter it like this: 5 by 2x cube, the capital X. Okay, like this. Okay, and now it's for all positive integers, so they will be asking you the interval starting value and an interval ending value and a step value also. Since this is integer, your step will be 1 because you need whole numbers. You can start from, it's a positive number, so you can start from 1, and maybe for the beginning you can end at 10. Okay, so this would give you the different values of f of 1 up to f of 10. So you would be able to pick a value from there which is not a perfect cube. That is what the question asks for. But you need to show a few values for which it is a perfect cube also. For example, f of 2, when you calculate it, this is going to be -8, which is a perfect cube. F of 3 will give you 8. Then if you are doing for f of 4, it is going to give you 64. And f of 5 is eventually going to give a non-perfect cube number, which is equal to 175. Okay. So the different trials over here gives you 1 mark, and the counter example gives you another 1 mark. And you should state that for all proof questions you should have a statement of proof. 175 is not a perfect cube, therefore then you can repeat the statement over here. Therefore f of n, the statement that f of n is a perfect cube for all positive integers is not true. Okay, so the SOP, the statement of proof, carries the last mark. Okay, so that is the first part. So in the second question, we need to prove that this statement is true for all real x, that is x plus 1 the whole square is greater than 6x minus 4. So in all such questions, what you need to do is you need to expand it, rearrange it, and try to bring about a perfect square. You will understand the reason for that shortly when we reach that step. So we expand it, we rearrange it. So I bring the 6x over here and the -4 over here. So that is plus 2x minus 6x plus 1 plus 4 greater than 0. So I have x square minus 4x plus 5 is greater than 0. Now to make it as a perfect square, I split this 5 into plus 4 and plus 1 because this term would make a perfect square. Okay, so that I have x minus 2 the whole square plus 1 is greater than 0. This is what we need to prove. So if this proof is correct, the question is also correct. That's what it means. Okay. Okay, now in this part, this is already a perfect square. Any number, if you take a particular number and take a square of that number, even if it is negative, that is going to be positive always. So this is positive, or the minimum it can go is 0. So this is positive or 0. And then to that positive or 0 number, if we add plus 1, this is always going to be positive only. Okay, so we can say that since x minus 2 the whole square is greater than or equal to 0, x minus 2 the whole square plus 1 is always greater than 0. Okay, so this statement of proof has 1 mark. Now the next mark over here is for this particular method where you do the perfect square thing, and the first mark is for the rearranging all those things. Okay, so this is how you get the 3 marks. Okay, I hope you understood. Thank you.